Good afternoon. Thank you for having me. It's really exciting to be here. I was speculating in the very beginning how far you have to move away from Vienna to get invited as a speaker into the Visual Computing Trends Symposium. I wanted to plot this as a scatter plot, but then I thought that's too old-fashioned and I won't do that. So yes, I studied here in this beautiful city and worked for Werner Pugathofer for quite a while. Then I became professor at TU Graz, another beautiful city, but very recently, through to the generosity of the German Alexander von Humboldt Gesellschaft, I decided to move to University of Stuttgart and actually not become the successor of Tom Ertl. He just happened to retire in the same year when I came. Probably I scared him away. So this is where I am now. Quite an interesting deconstructionist building in Stuttgart that we have. Only the roof is leaky, but otherwise it's really nice, and it's a kind of family reunion here. I've talked to so many people that I spent a lot of time with. I also dug up some really old stuff. So augmented reality was already a thing in 1996, and most people, except me, have not kept their 320 x 240 QuickTime movie files of the days. It looked like this. Yeah, and thank you, Werner, for paying for the Indigo, SGI Indigo Impact with video option, because that made it possible to actually have that kind of video. Analog, of course, analog input and output. So yes, we had interactive augmented reality, stereoscopic even back then. That was when computers were still paid in shilling, so it was, I think, 400,000 shilling for the workstation. And it was even collaborative, so this is what you see here. So by the way, this is a paper with a guy called Löffelmann. Most of the people will know that he's now Helwig Hauser. And it was scientific visualization that we did back then, right? But this is mostly a blast from the past to show you augmented reality has been around for 3 decades now. And a lot has happened since then. But then I was also reminded by how visual computing trends came to be. And when Werner was still scientific director, there was the insistence that if you speak here, you have to give a lecture, and you can only talk about your own work for approximately 10% of the speaking time. And that means you have to summarize the field as opposed to just take a face bath, some sort of personal trip. So of course, since Werner was my boss, I have this still in the back of my mind, and I can't escape it. So I'll actually try to only speak about my own work for 10% of the time. Let's see how it goes. Anna didn't do it. Anna knows that as, oh, here you are. You knew this and you didn't do it. Yeah, so as you all know, my topic is augmented reality, and you're all aware that a lot is happening in the market here. There's great new stuff coming out. Sorry, Daniel, I put the Apple Vision Pro here, not the Snap Spectacles, but I change it. But anyway, my point, so I had this radio interview just an hour ago, and the journalist asked me again, like they always do, so when will we be using augmented reality on a daily basis? And in order to answer the question why this is taking so long, I always invite people to think about which technologies were an instant success. We have graphical user interfaces, since the 1990s, mobile phones a decade later, touch screens, and so on. How long did it really take to mature? If you think about the very first mobile phone, that's the Motorola Dynatec on the upper right-hand side. I believe it was 1983. Now, and this is a cucumber, at least in German, we call it Gurke. Yeah? That if you ask a person owning a Motorola Dynatec in 1983, well, you would have had to go to Japan where it was launched, but anyway. So to predict the future, like, will everybody have a Motorola Dynatec in their pocket in the future? Yeah? Will there be 10 billion Motorola Dynatec in the future? Probably the answer would be no. And if you ask them what they would be going to do with it, they would not come up with anything else but voice telephony. Now, who has a kid in this room and the kid is using the phone for voice telephony? Raise your hands. Okay, I think you get the point. So, technology is not a single track thing, it's a convergence of many things, and only if the time is right and the clever companies knows what to do with it, then you get results. Look at the Apple Newton. Who remembers the Apple Newton? Okay. So in my class, nobody remembers the Apple Newton. It's a mobile computer, right? And I would claim that even though Apple must have lost a lot of money on that Newton program, it put them in a position to launch the iPhone in 2007, which is more than a decade later. And now, of course, we have the Apple Vision Pro, and it's great, but also super expensive and cumbersome. We have these significant investments on the side of commercial companies to commoditize certain technologies that would not happen by itself. So it's really hard to make these predictions, and you have to be patient. And there's always this question about the killer app of augmented reality. And again, I would like to draw an analogy to the phone, to the smartphone. So my phone has an app called Phone. That should already tell you something. Apart from the Phone app, there's 99 other apps installed on my phone. And it definitely does not have a single killer app. I would actually claim that the phone, the fact that I have a sort of portable computer in my pocket at all times, is a killer platform, or call it killer service, killer ecosystem, whatever you want. And this is how we should think about other digital technologies, and in particular media technologies or communication technologies. So now we have the case for Apple Vision Pro. I had to get ethics approval for taking this picture. So this is of course video see-through now. Video see-through is a commodity. We have a Meta Quest 3 now. The 3S is only $300, right? So that's super great pricing. And video see-through is now a standard mode of virtual reality. It's just a byproduct of virtual reality. So we can deliver augmented reality today in a good quality, but of course not for full-time use. Nobody will be wearing the Apple Vision Pro the whole day long. And for it, sort of improving the field, for experimenting, for research, I think that is a very nice situation. I'm much happier now with this sort of availability of technology than I was ever before. In the future, we may have optical see-through glasses, and I'm checking with Daniel Wagner, they're back in the audience, but this is a picture that was taken of myself, so there's no problem with IP rights on that picture. That's a the Snap spectacle glasses, which are optical see-through. You see that a really nice form factor is already possible. But a really long battery life is not really possible yet, but we'll see. So that is for other sort of threads of research to improve. But if you go walk on the street wearing that kind of thing, I believe you could be called a fashionable person, or trendsetter, let's say. Yeah? So we have reached a good enough state. In the near future, what might happen, and I mean this is not already the outlook of my talk. So Apple is pitching spatial computing now. You've all seen that, the Apple Vision Pro. So what are they selling you? Replace your $3,000 MacBook with some $3,000 XR glasses, And the net outcome of that is now you get a huge screen wherever you want. Huge screen primarily for 2D productivity applications, not so much 3D, not so much games, very different from what Epic is pitching. But I mean, that's fine. That's maybe the most realistic projection for a business that somebody wants to develop in this decade. Coming from Apple, they might have considered that carefully. A decade from now, assume that all these products from Apple, Meta, Google, and so on are successful, and we also get optical see-through glasses that can be worn all day. Then what might happen is the continuation of what Apple is proposing. Ditch your phone, get the glasses, put them on. You don't need a phone anymore, the computer is your glasses. By the way, there's interesting research, for example, coming out of Gordon Wettstein's group in Stanford about autofocals, so prescription glasses that are active with liquid lenses that can be used both for nearsighted and farsighted dynamically based on depth sensing. These existing technologies, there's a big market for that that can potentially be a real multiplier for sort of bringing this new kind of technology to larger audiences. I'm not a commercial person, but I have a feeling that this might be an important aspect. So what am I doing with this? I'm interested in situated visualization and situated instructions in particular. So assume that augmented reality replaces the smartphone as the dominant form of situated information access. That would be really nice. No more QR codes to scan. It will all be sort of happen on the fly through sophisticated sensing. The content would be tied directly to the physical object, so you no longer have this problem of, there's the bus timetable printed here. You call up the Stuttgarter Verkehrsbetriebe traffic app and try to now cross-reference what's going on there. All of that could be done for you. Explanations and guidance can now be provided directly at the task location. And that's what we do with the 100+ apps on our phone anyway, but in a much more cumbersome and sort of fragmented way. You do not need to consult a separate knowledge representation anymore. Cognitive separation might be minimized, and there are studies that show that this actually does have a beneficial effect, although your mileage may vary. So just to give you, I've done many of these experiments, just to give you some example of a situated visualization. Here's guitar learning. So what you see here is guitar tablature and then some cues based on finger poses and so on. For a person learning the guitar, also with a MIDI pickup, you find out whether they actually did it correctly or not. So it becomes this sort of Guitar Hero type game where you can actually train. Yeah? And this is situated information visualization. It's relatively abstract information, but it has a spatial interpretation on the strings of the guitar, and it's interactive. Yeah? So there are many of those opportunities where this kind of visual situated visualization can help. Or here's a slightly more involved example. Internet of Things. We all know that we get all these smart devices now. You have smart window blinds and whatnot. Yeah? But they all come with their separate apps, or even worse, separate remote controls. And you have a zoo of remote controls of various forms. Now just think about if you go to a basement where you have heating, power, wastewater, and so on. And in the future, these are all going to be smart meters. So now how do you get some sort of unified inspection and then also maintenance interface? Yeah? Let's assume you can get the 3D scanning part rather cheaply. I mean, that is technology that exists. There's simultaneous localization and mapping, which all these devices do on glasses, also on robots. You might have equipment databases and so on. So we said, well, let's try and do an augmented reality interface with that. And this is the actual basement in Graz with actual sensors that we placed there. They didn't come with the instruments. But you now get sort of situated visualizations based on proxemics. You go close to something, you get a visualization. The visualizations may not be super pretty at this point, but they are generated automatically using a grammar of graphics type approach, like you would do on the desktop. And the idea is that this would also be unifying, so we assume that you have a MQTT protocol over the wireless network, which is a home automation standard. If that is available, then you get this kind of visualization, and it could be varied much more. We call that software RegRug. It's my new favorite software toy. Software framework that supports Internet of Things and augmented reality, and the key idea here is to not reinvent the wheel. So you have this entire stack of IoT software, such as Node-RED, for example, that's an automation framework, and network protocols and so on. You do visual programming with a nice web-based editor. And then there's this other area, the augmented reality domain, with its own set of tools, such as the head-mounted displays, say MetaQuest or HoloLens, tracking, SLAM, 3D gesture recognition, Unity game engine, visualization tools, and so on. You know, if you combine that together, it's very powerful, but not very easy to learn. So what we did is we unified that basically using event-driven functional reactive programming, which is a fancy term for saying data flow programming that all the visualization people in the audience should be familiar with. What you see on the right-hand side is this is actually brand new. What my PhD student in Stuttgart sent it to me yesterday. He can render the Node-RED data flow that is in 2D as an actual 3D representation in Unity. The kick here is that you see that this is Unity on the right-hand side. So we can now even do this sort of interactive flow construction potentially while wearing a headset. Okay, so that's a powerful software framework that I really like, but then I'm reminded that I shouldn't be talking too much about my own work. So I'll move on to somebody else's work. This year, Ben Schneiderman is not here. He was here, 6 years ago, I think? Okay, so you have to make do with me instead. But I have read his new book. We now have powerful AI co-pilots for everything. Artificial reality intelligence is the new fad, right? Everything's better with AI bacon, or it seems like that. And then there are some people that are concerned, and I mean, I made these slides, of course, before I heard your talk, Anna, because you both reflected on the same theme. We need human usable AI. That's another way of putting it. Yeah? Schneiderman calls it human-centered artificial intelligence, or HCAI. And one of his key theses is that AI is just a bunch of more powerful tools, but now if I give you a really, really big, powerful hammer, you have to learn to be careful with it. Yeah, we have to first make these tools safe and then apply them in an appropriate way. And I mean, I think that is happening to some extent right now, but it's very much focused on text due to the surge of LLM technology that we've heard about, or I'm sure you're aware of it. And then since it's text, it's sort of centric on the desktop, writing, coding, these are the things that are primarily considered. And augmented reality, of course, can provide interfaces that are away from the desktop in situations where you don't have a desktop and where you don't want a desktop. And this is how this goes together in an interesting way. So maybe I skip over that. And I'll give you a use case. I'll stick with these instructions, in this case for assembly and maintenance, guidance, providing guidance for assembly and maintenance. So you would want to do things like highlight a particular object that should be handled somehow, provide dynamic video insets showing you the exact representation, or also other forms of instructions. A good one is, as you see on the lower right-hand side here, X-ray vision. So the superpower that allows you to look inside things and see exactly what you need to see, because that's the hard part. Yeah? So this is what you see with this example on the lower right-hand side. This is a coffee maker, and you're supposed to remove the brewing unit, and there's a lid on the right-hand side. I believe the lid will come up. No, I think in another segment of the video it's open then. Or it's text again, but then if you just put text labels like you put in medical illustrations, and it looks terribly incoherent over time. So this is the bad example. And the good example is what I show on the right-hand side. So this is solving the layout problem dynamically in 3D, and the number of problematic situations where you sort of arrive at a local minimum in this optimization space and then get stuck there isn't really is much reduced. Yeah? Chances are that that the labels make a good so are very legible all the time. But these are all conventional algorithms that can benefit from adding artificial intelligence technology of the sort of new flavor that is now available into this domain. And if you think about this assembly guidance problem, the minimum that you've just seen in these video figures is you have a visual model of the parts, so you know where and how to overlay things. You need an assembly plan that's more abstract information, like which part has to be mounted after what other part, are there any fasteners that have to be applied, and so on, what kind of tools should be used. And then you need an application that actually presents the visualization and the interface in augmented reality. And without having artificial intelligence available, you need to bite the bullet and engage in the manual creation of all that input data. So not only the coding, but also the content generation, because the content may only partially be available from existing sources. The company may have CAD files for their products, but the question is really whether they have the assembly plan and so on in any other form than text. There are usually specialists who write those manuals who may not even be using the original CAD files. There's also a lot of messy production going on. So that's for the sort of authoring phase, and then the delivery phase that has been demonstrated numerous times is that you have an augmented reality application showing the stuff that you should be doing, but with manual advancement through the assembly plan. So there would be a next button and the next button and the back button, and if you make a mistake, you would be on your own to figure out that it's actually deviation from what is being shown to you. Yeah? With artificial intelligence, we can do better. We can detect if a step is completed. We can detect if a step was completed in the right way, so you didn't screw up while you were doing it. And in order to do that, you can use basically object detection technology that is established. It's the same kind of object detection technology that does, you know, that detects what bicycles are very popular and other things, but enhanced to deal with this sort of problem of the parts in assemblies. And I'll show you what that could look like. So what you see here is a real case of assembling a drawer from IKEA, and the white piece of wood has been incorrectly placed. It should be rotated by 180 degrees, and that's a mistake that I made with my drawer. So my student took my narrative and implemented a fix for that. And the details, of course, between the right and wrong orientation are rather subtle. Object detectors cannot easily grasp that, even though they have been trained with these. If you just show them the individual stages of the assembly, that is not enough. Yeah? So what would you do about that? Well, first you need to generate sufficient data, and this is where I have my first reflection about the artificial intelligence technology. I was scared for a couple of years, but then it turns out it's in the end a universal function approximation. You just have to give enough examples of how the function works. And what do computer graphics people do? They render images to supply more functions. So we actually generate data from the CAD models of the assembly parts, and then with random hands and random backgrounds and so on, just to confuse the system and sort of support it in ignoring those things. So that all goes into training of a YOLO object detector that is sort of refined with that, and then you get this kind of application. And now comes an interesting part. That would normally go if you have an assembly sequence. You can maybe teach the system that there's more than one way to assemble something. It's basically a directed graph, not a list of assembly steps. But errors are, of course, not covered. Now, if you look at sources, and we've looked at like literature from industry processes, from logistics, what kind of errors people make, it's usually placing wrong objects in the right place, placing objects in the wrong orientation in the right place, and so on. There's only a few things that can happen, and these can be sort of enumerated from the correct assembly steps as variations that are erroneous by systematically saying, okay, if I turn this around by 180, then it's wrong, and so on. And so we also get examples of all the errors. And I think this figure is showing that something that you might be familiar with, right? There's this screw and there's two drill holes in the IKEA furniture, and somebody, that would be me, puts it in the wrong place. Yeah, and we have a system that can sort of look out for that. Yeah? Then you get the typical neural network architecture, which has been augmented with a method based on contrastive loss. So the idea here is that you repel samples from different classes and pull together samples from the same class, so the discriminatory power of the network is thereby enhanced, even if the differences are rather subtle. Yeah? What you want to do is, I think we've seen a similar clustering image in your talk, but it's always the same. Without contrastive loss, the system would probably correctly identify many cases, but its discriminatory power is much stronger if you help it with this strategy of strategically repelling and pulling together samples. And now this contrastive loss is combined with a new stage in the object detector that is really only using the previous state as an additional prior. If you already know what state you're in, the number of subsequent states, both correct and erroneous, is much smaller than the total number of states in the system. And so if you know the history, then basically the system becomes now able to reliably discriminate what you have done and also whether this is correct or not. And the result you've already seen in the video, it can do this thing with the two drill holes in a rather nice way. You still need to feed it the actual assembly graph, and that can also be supported with additional AI tools. So let's still assume we have machine models from the CAD data. And what you can do is you can record the demonstration that the person is doing. But we do this in this work here that was published earlier this year in a virtual reality setting, where we have an easy time recording the hand movements, the tool use, gaze, speech, all of this is sort of relatively noise-free if you do it in virtual reality. But we got real industrial experts to try it out, who said that, yeah, this is like if they are giving a demonstration, it would be a similar thing. So
hand movements, machine part manipulations, gaze data, as well as recorded speech for adding detailed comments or additional information. Detailed.
And so the expert, in this case one of my students, can demonstrate this sort of process step by step. manipulate the individual parts. This also extends to hierarchical model parts. So the system would, for example, know, or you are, as the user, are able to disambiguate whether you're using, you're moving the phone or you're moving the cover of the phone and the phone separately. Hierarchical assembly, which is important for those things.
System enables authoring of instructions by demonstration, utilizing virtual replicas of actual machines. We support 3D models generated from CAD data and can track room-scale activities.
And so this final result is then delivered after automatic segmentation. This is where the AI comes in. So you have these individual activities lined up, and that lets you also make fine adjustments. Like you did something twice, so you did it wrong the first time, you can delete that segment and so on. It's a little bit like video editing, where you're also working with shorter video clips. And then ultimately this presentation can either be delivered
from recorded instructions.
VR or AR.
We introduce a user-friendly interface for post-processing and editing tasks directly within the VR environment. We indicate the spatial distribution of work steps as activity clouds. User navigation through complex room-scale instructions is assisted.
Yeah, so the final delivery, of course, is intended to be in augmented reality, but this wasn't included in this study here. If you have the problem with augmented reality is then you need the object tracking of everything, not just the detection. I showed you the YOLO architecture for detecting the objects, but not tracking like 25 of them at the same time, which is still kind of challenging. Yeah, and here's the resulting presentation, again in VR, but it still it already allows what could be called real scale training, right? You're not watching a video on a tiny screen, you have it in sort of full size in front of you, also for trainees. And adaptively, you can repeat procedures, you don't have to go through it in one go.
Head and hand poses can be used to animate avatars for detailed tutorial videos.
So the motion capturing gives
recorded data can further be used for a range of applications, including process optimization and text exporting for printed handbooks.
So the avatar would be automatically derived from the performance that the user is giving. Oh, I did it again. So I promise I won't do it again. I'll look into the future and talk about the incorporation of AI tools for augmented reality content, and I'll talk about other people's stuff, which is super exciting, all brand new. Unfortunately, the papers on arXiv are popping up at the rate that I have a hard time keeping up reading. I don't know about you, but I think we all face that problem. But it solves many of the problems that have sort of held back developing these kind of augmented reality applications in rather nice ways. And so I'll make some attempt to explain to you some of my understanding on these artificial intelligence tools, and that some of you may be much more experienced than I am. But anyway, here's my 2 cents on how this could be used for good. So it's clear that the large language models are one of the key assets in that game. With a large language model, you can do amazing things. You write a prompt, and then what you get as a result is a response, a textual response, that is not only good for chatting about whatever, but also for jobs like, for example, you have the expert demonstrating an assembly sequence. Text is transcribed, the voice is transcribed into text, but it's very incoherent with stuttering, maybe in dialect, maybe not nice, presentable, sort of clear instructions. So you tell the LLM to summarize that text and break it down into individual short sentences and so on, and this is what an LLM is already doing a good job at, emulating sort of human utterances. Also, large language models are used for software development. This goes as far that some people say we shouldn't be teaching our students programming anymore because the AI will be doing that. But anyway, it accelerates dramatically what you can do also at runtime. And at runtime is an important phrase in the augmented reality business, where you always have to assume that you have these unexpected situations. Now, under the hood, there's some technology going on which will then be relevant in the things that I get to next. How much time do I have left? The LLM breaks down the input into tokens. These are the things that you pay for at OpenAI. That's more or less a word, give or take. And for each token, a so-called language embedding is generated, which is really just a vector of values in the range 0 to 1, where every value corresponds to some semantic concept. And the embedding indicates how well a token matches that particular concept. And now you're sort of redirecting the intelligence in artificial intelligence to your choice of concepts, whatever that could be. Of course, the large language models have a vast knowledge base from which these concepts are derived. The thing that is actually done to search through that vast space is just the similarity of two embeddings, and that's, for all the computer graphics people here, that's a dot product. I mean, it's a high-dimensional dot product, but when I realized that, I felt so at home that I said, carry on with this. Yeah. Obviously you have to store all that information somewhere, so these vectors and the value of values in the range 0 to 1 are stored in a vector database, which is essentially just a database for this kind of data that allows fast search and retrieval there, and also get the original text back, of course, that was associated with that. Yeah? And this is a key mechanism, rather simple one, how this works. But that's what everybody seems to be much focused on. The large language models, and there are these other models, foundation models if you want, in particular language vision models that are not as prominently discussed, but probably even more important. So here you show a picture to the machine, and rather than tokenizing the text words, it maps image pixels to an embedding space. And there are these tools such as the flavor of GPT-4 video, or Lava, that's an open source one, or Ferret, that's a smaller one, that do that with images in a very sophisticated manner. And then you can have sort of downstream applications for that would include summarize what you see in a picture. So picture to text is one of the most widely known applications of language vision models. It can explain to you what happens in a picture. By extension, you can also make it explain to you what happens in a video by just showing like 5 frames per second, and then ask what changed since the last picture. It's all prompt engineering. That's another big realization, that many of these techniques in the end refer to just prompt engineering. But then there's more sophisticated applications such as semantic segmentation. So the segment anything, this is a very recent work now, I believe by Google if I'm not mistaken. It is essentially taking the output of a language vision model to cluster groups of pixels with similar embedding, and then suddenly you have solved the segmentation problem that has plagued computer vision for decades to get sort of a fast and usable version of that. Yeah? And as you see, this is pretty sophisticated. So now you know what the entities, where entities are in the object, and of course you have the semantic, the language embedding to explain them. And from these fundamental tools, large language models, language vision models, more sophisticated tools can be built. There are even frameworks such as LangChain now that allow you to orchestrate together AI tools, and a lot of the publications that are coming out in that space are not creating new models. They are using the models to produce new kinds of results, again, which is a very important realization. So what we want, and we've seen that before when we discussed, for example, the assembly guidance, we need a representation of the real world. In computer graphics, this has been traditionally in the form of a scene graph. You know, back in the old days when Gerd and myself were sharing an office, we used Open Inventor, yay, or Performer, or Open Scene Graph. Now we have game engines like Unity and Unreal that essentially use the same kind of idea, only in a modern disguise. Which is a graph that imposes a hierarchical organization on the sort of entities that are supposed to be in a virtual scene. And these would contain nodes for geometry, appearance, behavior, light, and other stuff. Yeah? Mostly with the objective of rendering and animation. This is what came out of this computer graphics branch. Turns out the AI robotics community has redefined the term without ever referring to the other, like 20 years older scene graph. I call it AI scene graph for lack of a better word, because the literature just calls it scene graph in the space of robotics and machine learning. You start, what happens here? You start with a conventional SLAM algorithm to get some geometry. Yeah, so you have one of these scanners, usually consisting of camera and inertial measurement unit, like in the headsets or even on your phone. An iPhone will work very well, and it gives you an RGB or RGBD sequence with depths. Yeah? From that, you track the camera and you build a 3D point cloud. So you incrementally get the 3D point cloud. Now on each of the keyframes that are required there, this is the second step in the middle, you can apply SAM or some sort of semantic segmentation, and that gives you semantic feature vectors for groups of pixels like we've just discussed. So they do that now with an open vocabulary language vision model, which means there isn't a predefined restricted set of concepts that are applied here. The concepts are chosen dynamically based on what appears in the scene, which is a curse and a blessing at the same time. I'll get to that. Yeah? But it's definitely very powerful. And then all you have to do to upgrade that to a 3D AI scene graph is to build a 3D map out of that by back projecting all these segmentation labels to a 3D point cloud, and again refine the clustering, the segmentation there to arrive at sort of three-dimensional objects with semantic features annotations. Yeah, this is what you see on the right-hand side, a map of 3D objects. So that's really amazing, because we've only put together tools that were already available, but of course that is downplaying the significance of that. I would really call that a seminal step forward. Yeah? The semantics still needs to be refined. The AI scene graph, so the AI scene graph now has objects as nodes, but what we don't have is we do not have relationships as edges, which is what the full-blown knowledge graph would typically demand. Yeah? So the objects can be directly taken from the 3D map. The semantic context comes from piping the whole thing through an LLM and ask it to describe the objects. And then you can query the LLM about the relationship. So maybe you look at these prompts here to understand what's going on here. So the data from the sort of object-only scene graph tells you that object 1 is a stool with position such and such, object 2 is a carpet with position such and such, and the question, the actual query to the LLM is, what is the relationship between object 1 and 2? And then it says object 1 is on top of object 2. So for example, topological relationships are inferred by the LLM. Yeah? At this point, you need a large one that has reasoning capabilities. The smaller ones, like Olama, may be lacking in that department. So you end up with also edges as relationships, and that, of course, now is a very powerful structure which has a sort of a rich semantics, but it also has the original geometry. And now you can think by yourself about the typical applications that you would get from this sort of approach. Here's one from the original concept graphs paper, which is done by a team of very famous roboticists. And I think it has 17 authors or something like this. So there's a lot of work that went into this. But you can now, for example, have a little robot and that has scanned the environment. And now you say, my wrist hurts from using a screwdriver all day, anything to help. And the system decides, robot, go to object 18, a power drill, which just happens to be there. Yeah? So you can ask for more sophisticated things. This is another example that was published last year. XR objects, in this case a cooking scenario, where it scans the objects and then retrieves from the sort of knowledge that is in the large language model suggestions, or there are some hand-coded things like these timers that can be attached to cooking pots and so on, because it can sort of draw from a repertoire of things that come out of the knowledge of the large language model. You can even go to adaptive instruction generation. I mean, this is a rather involved graph, but I mean, you have the reference if you really want to study this carefully. What they are trying to do here is observe a person doing thing and then ask the LLM via sort of video interpretation, what has the person been doing, and you arrive at an instruction sequence. And if you're lucky, you can even then later have a person sort of consume these instructions, try to repeat the procedure, and if they make a mistake, you ask the LLM, did the person do it differently than the guy before? Yeah? But as long as the knowledge that is represented in that system only comes out of a vanilla large language model, it will not be very specific for this for this kind of problem. Yeah? The large language model is not powerful enough. There will not be enough annotations of video of a person cooking pasta. Yeah? That's not the kind of content for which the large language model is trained for. But there are techniques in the area of large language models that are designed to deal precisely with these kind of shortcomings. And now I'm getting to the stuff where this is basically the PhD topics of some of the PhD theses that I'm supervising in Stuttgart now. So this is really ongoing work. Retrieval augmented generation, that's the sort of most established way of fixing this problem of the foundation model not containing the specialized knowledge, which was, by the way, also mentioned by, I believe, all three speakers before me today, the specialization problem. So what happens here is that you have a knowledge base that is separate, that doesn't come from not necessarily from a whatever collection with machine learning, can be Wikipedia or any database that you want. Yeah? The database that is proprietary to your company, for example. The format in which this is exposed to the large language model here is, if it's text, then it can be indexed as a language embedding. And now what happens is when the question comes in, you first have a retrieval query where you do this dot product matching to find sort of in your proprietary knowledge store relevant information that should be added to the prompt in order to then give the large language model the context that is necessary. Yeah? And you can't feed it the entire database because then the context window would overflow. You have to specifically find out the relevant information, and this is what the retrieval augmented generation does. And then with that background knowledge, maybe the extra instruction of only use facts that come from the knowledge base, don't hallucinate anything yourself. Yeah? You can cross your fingers and you get hopefully a higher quality answer. That's not the end of it. You want better retrieval queries than just the dot product matching. I mean, that's too cheap. If I understand dot products, it can't be so sophisticated. So instead, a knowledge graph is built a real one that has language embedding and relationships. That is, of course, a more involved sort of preparatory step, but it now allows you to not only retrieve by similarity, but also indirectly by the relationship. So you have similarity match, then a relationship to another concept in the concept graph, and sort of the graph neighborhood is also delivered to the RAG prompt, which is then fed into the large language model. And with the help of that, you can now support more complex queries better. And in particular, remember, we already built a knowledge graph. We built our AI scene graph, which essentially is a knowledge graph. So somebody has to just feed that in there. We're just trying to do that. Then there's this aspect of knowledge or scene graph generation, where the problem with the open vocabulary language vision model is that it is not always returning the useful aspects. That will be very generic if you're mostly interested in cooking or repairing stuff. And this will just suddenly tell you, well, there's also a curtain in the picture and it has a beautiful flower pattern, then you're not interested in that kind of information. You want or it tells you this is a beautiful screwdriver, it has a red handle, but you want to know whether it's a Phillips one or a standard one. So you need domain-specific fine-tuning, which again mostly means creating proper few-shot examples to augment your prompt. And of course that can be done with if you know the domain, you can find ways to do that. Also, chain of thought prompting is another technique where you tell the system what kind of conclusions it should be drawing. Basically, you tell it, if this is the case and that is the case, then this is the conclusion that you should draw, and that's just part of the prompt. And in that way, you can find you can tailor sort of output that is relevant to your application. Now, the one thing that I haven't touched upon is how would you deliver that? I do not want to have the AI continuously whisper into my ear, right? I have an Alexa-capable Echo Spot at home. I tell it to play music for me, but I don't want to have a conversation where every hint that I get in real life comes with audio. Instead, it should be visual. After all, we are at the visual computing symposium here. So you have to output the results in a visual way. And of course, the text prompt, just putting a text prompt insert like you saw in this XR objects video snippet that I showed you, is not what I have in mind. So we've recently worked on a catalog of augmented reality patterns. Here, these are various popular forms of augmenting objects. The cylinder, the yellow cylinder is always the physical object. And then there are many sort of embellishments. And these can be automatically generated. Now we can put it all together. Grammar of graphics generates the visualizations, and the code for the grammar of graphics is generated by the LLM via the mechanisms that I've described. Then we can roll the smart objects into that as well. For that, mostly you have to identify where the smart objects are in the environment, which hopefully the scene graph scanning will let us do, and then with some sort of clever support, you can go to the network, find out what kind of network traffic from the sensors is there, and match that up. So this is something we're just trying to do, that it would automatically identify. There's a smart oven in my kitchen, and on the network there's traffic about Miele Herd number so-and-so, yeah? And somehow by virtue of knowing what a herd is, the system would be able to put that together, and then you can finally create remote control interfaces with augmented reality for all these sort of parts of your smart infrastructure. And the difference to what I've shown you before is that here the world is no longer static, right? The objects are dynamically responding to your inquiries. So that brings me to the end already. I think intelligent instructions would be like the killer idea that can make augmented reality really popular, because we look for information on the internet all the time on our phones now, and this could be sort of integrated in what we do. That would be an example of what Schneiderman calls the HCAI super tools. And that's a very different AI application from the one that my son tries to have his homework written by. It's the kind of AI that would make Google search on your phone unnecessary. So I think the Apple spatial computing idea maybe, hopefully it will help establish XR technology into the mainstream, but I don't think it will be the sort of long-term thing we want. What I want is not spatial computing, what I want is situated computing. So with that, I would like to acknowledge all my collaborators from Graz and Stuttgart, and thank you very much for your interest.
So thank you, Tito, for your inspiring talk. Yeah, are there some questions? Real ones, not virtual ones. Yeah?
Okay, first of all, thanks a lot. It was a really interesting talk. My background is I'm a teacher at a high school at the HTL for game development, and I was wondering to simplify for these projects that you just showed, the game engines, Unity and Unreal. If you don't want to go the AR route, but just be in a virtual environment built with Unity or Unreal, you would probably have a really easy time feeding that to the AI because you already have the perfect scene graph, right?
If you want to use a scene graph that is created in that way, then yes, but it's probably much easier, and people have done that, generate the game content through generative AI. There are also great 3D generators now that don't even draw from sort of real-world pictures, videos, or whatever, but just from fictional descriptions. That is probably even more economical, unless you really want a shooter to play in your living room.
What I meant was if I want sort of LLM assistance from virtual world, then I could just take the scene graph that the game engine builds for me, and that would instantly. That would be much easier.
The question is the scene graph that is in the game engine, does it have any semantic tags already or not? Yeah? If it doesn't, you could potentially try to use these techniques to build them, but maybe there are cheaper ways of doing it because it's all digital, right? This whole procedure deals with the lossy acquisition from the real world. And inside the game engine, you could probably find more direct ways of getting a similar kind of outcome. But yes, games that have sort of adaptive behavior to what the user does will definitely benefit from that. So they won't be so repetitive and boring anymore. That's a good idea. I should take note of this. Thank you for the question.
I said it first. Thank you very much.
So, do we have other questions?
Thank you very much for your very lively and insightful presentation. So, my question is more direct towards the more information visualization perspective. So, as we're using mainly 2D visualization techniques, it feels a bit unnatural then to use them in our 3D environment, and so that's also what I observed. That we mainly use this billboarding, putting the 2D visualization techniques somewhere in space then. So do you think that there is a need to create completely new forms of visual representation that are really taking advantage of that context in situated visualization?
For the applications that relate to the physical environment, I think yes. We will have to have, new is maybe too strong, but sort of adjusted designs. Yeah? So all this entire catalog that you see here is not meant for visualizing abstract information that doesn't have anything to do with the yellow cylinders, which stand in for whatever object is in your environment. These are all visualization techniques that would, for example, show you a heat map on the surface of an object, so you can see that I'm sweating or something like this, yeah? Or my body temperature or whatever other feature you're interested in. If you want to go to the more abstract domain that is not related to physical reference in the environment, then I mean the technical term for that would probably be immersive visualization, not situated visualization, even if it's in AR, and then established visual encodings are good. Yeah? Then we're back to this spatial computing where you have some flat surface on which content is projected, so you do not have to carry your laptop with you around anymore. And that's probably a reasonable thing too, only much less sort of exciting than the sort of adaptive and context-sensitive things that I focused on. So I think both will exist.
Okay, another question maybe. Right.
So thank you as well. You said from spatial computing to situative computing, but do we agree that not every spatial computing application now will be superseded by situative computing?
No. I mean, this is pretty much Wolfgang's question as well, right? Now you use abstract data visualization and applications that have to do with abstract data for everything. And for the things that are abstract, it will remain abstract. But as soon as you have the physical referent somehow in your vicinity, you might benefit from some spatial or even situated presentation, and if only by sort of proximity. That is sort of the weakest form of tying it together. Yeah? So you have various objects, and then data is, for example, textual or some 2D InfoVis, but it sits where the object is, not in another place, which is what you have right now. That is, of course, a weak form, but it would be easier to achieve, and maybe that's actually going to be what's happened first, right? It's the no more QR code scanning. If all your supermarket products have barcodes on them, you could have an app on your phone that you will scan it and you instantly get the information, but nobody does it because the effort of holding your phone there and scanning is too much already. And if that happens as a byproduct of wearing your glasses, then you might just read that information, or maybe not if you don't care, right? So this whole entrance barrier is much diminished.
So I think we have some time left for 2 more questions, maybe.
Yep. Oops. Okay, thank you very much. You got me thinking a little bit, remembering with the times of study Stube and all that, when basically a lot of us were sort of working on a similar platform. And that sort of gave us the possibility to sort of have some benchmarks and work on moving a little bit forward. Do you think for reaching situated computing, and do we really need, should we need to have like something we could be really working sort of having the same platform, a little bit like a Utah Tipo type of thing for this type of work, so we can sort of benchmark and really focus on really moving forward instead of like the individual parts that we have now?
Well, eventually, yes, but don't forget that when we talk about an augmented reality system, it's really a system that is composed of many rather complex parts, and having benchmarks for that isn't what is usually done. The system is broken down into its parts, and then you have benchmarks for the individual parts, like, I don't know, object recognition rates. But that would only tell you how well the wooden board with the 2 drill holes and the one with the single drill hole can be discriminated. Then you can give a quantitative measure of that, some mean average precision, say. This is what the computer vision community does all the time. For the evaluating interactive systems is a known sort of huge challenge, and everybody who ever tries to publish at Chi or VIS or so should know that. because it's a moving target, right? There are so many factors that if you zoom in, you try something in particular, there may be confounding factors in other places. So the generalization that you can draw from such a study, or even getting your paper accepted with that study in it, can be rather painful even. And augmented reality is no difference, quite the opposite. We have difficulties. We usually publish these works in augmented in the XR research community, because the visualization research community, where some of that would fit, I believe, is not tolerant of technical difficulties that you have with your tracking system or something like that. You write that and they tell you you screwed up and the study can't be used. So the benchmarks for that would require that you have sort of an established consumer level product where some things can be taken for granted. We have commercial tracking solutions now in these headsets, so usually standard tracking situations are no longer the challenge. 20 years ago, when I was young in this work, that was what we focused on, because that's what the biggest problem was. That's no longer the case, but we're far from sort of system level benchmarks. I don't think we have them yet, maybe in 10 years.